All right, this is text problem 9-95, a suggested problem for lesson 17. So as we jump into our physics problem solving format, our first step is our read step. And as we go through and we read, we see that we have a collision between two identical billiard balls. We also see that we have information on the initial velocity of ball 1, and we have ball 2 at rest. After the collision, ball 2, we're given the magnitude and angle of our velocity, and our angle is with respect to the positive x-axis. Now we haven't covered conservation of energy yet, so our only option to tackle this problem is to conserve linear momentum. So our next step is to draw out a sketch of the problem. We already have a drawing, which is convenient, but for any type of conservation of linear momentum type of problem, we want to get in the habit of drawing a just before and a just after drawing. We do this just before and just after drawing because a lot can take place well before the collision and well after. So we want to look at just before they collide, looking at their velocities, and then look at just after as they begin to travel in different directions. So during our read step, we notice that mass 1, or billiard ball 1, has an initial velocity, and it's only in our x direction. So of course we need our coordinate axis system. And ball 2 is at rest. So that is the just before and then the just after. Now in our just after drawing, we have mass 2 going up and to the right. So it has velocity components in the positive y direction, positive x direction. Whereas billiard ball number 1 has a positive x component of the velocity and a negative y component of the velocity. Notice that I have my critical angles listed in reference to my coordinate system, which I have here. It's important to put that coordinate system on there because we're going to be dealing with vectors. And if we're dealing with vectors, we're dealing with components. It's important to note that when you choose your coordinate axis system, if you have the option to, in this case, our drawing has our coordinate axis system labeled for us. But if you have the option, try to align your axes with the motion of as many of the particles as possible in order to lighten the trigonometry burden on yourself. So if you can limit the amount of trig you have to do, it's going to make the problem a lot easier. So our next step is to list our given information. And we are given the initial velocity, here I'm listing just the speed, 2.2 meters per second for ball 1, and the initial speed of ball 2, which is 0 because it's at rest. Mass 1 is equal to mass 2 because they are identical billiard balls. This is going to be important when we simplify our conservation of linear momentum equation a little bit later. We're also given the final velocity, the final speed of billiard ball number 2. And we're given the speed, or the magnitude of the velocity, and the angle. And that's with respect to the positive x-axis. All right, we're almost done with our setup here. We have to make our assumptions. We're assuming that we have a closed and isolated system. The closed portion means that only objects involved in the collision, which are two billiard balls in this case, are the only objects in the system. There's no mass coming into the system, and there's nothing leaving the system, i.e. these aren't breaking apart into pieces that we're not accounting for. We're accounting for the total mass of both billiard balls. The isolated portion declares that there aren't any external forces or energy influences on our system. Notice we're not summoning any forces here. We're only looking at the conservation of the linear momentum in the initial frame, just before, and the final frame, just after. All right, next we need to list our tasks. First one being we need to calculate the final speed of ball 1. Next we need to calculate the direction of ball 1's final velocity, and that is going to be with respect to the positive x-axis. And then lastly, we need to determine whether or not this is an elastic or inelastic collision. Part C will be difficult for you all to do since you haven't learned about energy or how we can even conserve it yet. But we will get a chance to have a little sneak peek at what lies ahead when we get to Part C. All right, we're almost done. Last step before we solve, we have our physics step. And as mentioned before, during our read step, we have our conservation of linear momentum. So we have the sum of the total linear momentum before the collision and the sum of the total linear momentum immediately after the collision. And of course, don't forget our vector hats, and we'll need our linear momentum of a single particle or object. And we'll move on to the solve step. All right, time to solve. All right, so remember, any type of conservation law, whether you're conserving energy or you're conserving linear momentum or later conserving rotational momentum, it's important to know that whatever is the sum on the initial side must equal the sum on the final side. If they don't equal each other, they have different values, then that quantity is not being conserved. So either you've made an error, or as we'll learn in our conservation of kinetic energy, we may find that kinetic energy isn't conserved, and that will lead us to a type of collision. Again, Part C. So we have our conservation of linear momentum equation. And we remember from our reading of the course supplement on the conservation of linear momentum that the easiest way to deal with this problem is to break it into components. So let's do that. I have my same formula, except the only difference is that I have the sum total of the linear momentum in the x direction is equal to the sum total of the linear momentum in the final, on the final side in the x direction. And I do the same for the y. All right, so let's get to work. We have more information on the initial total linear momentum side than we have on the final side. So let's start there. All right, sorry for the change. I needed a little more space. So like I said, let's start with the initial side. We have our momentum of billiard ball 1, initial, in the x direction. We have the momentum, linear momentum of billiard ball 2, initially and in the x direction. And that will all be equal to the linear momentum of billiard ball 1 on the final side in the x direction, and the same for ball 2. As we look in the y direction, we have the linear momentum of ball 1 initially in the y direction, ball 2 initially in the y direction, and it looks like my mask got chopped off. And now I'm in a different color. we have the linear momentum of ball 1 in the final side in the y direction, and we have the linear momentum of ball 2 in the final side and in the y direction. Now we can put in some of our initial knowledge. I'm not going to put in any numbers yet, but I do know that ball 2 is initially at rest, so it will not have any linear momentum. I also know that ball 1 was only traveling in the positive x direction, so it will not have a y component of the velocity. All right, so let's rewrite that and put it in terms that are more familiar with us and the given information. Now at this stage, notice how I got rid of my x component of ball 1's initial momentum because it's only traveling in the x direction. So I put in the magnitude of the velocity. Here I left in the x component because we will need that for later. But for the x component of ball 2's linear momentum, final linear momentum, I put it in terms of the magnitude of the speed or magnitude of the velocity times the cosine of theta 2. So let's look at why I might have done that. So we have our hypotenuse here as the magnitude of the velocity in the final frame. And that's going to be broken up into components. So in the horizontal direction, or the x direction, we have v2 fx, and we have in the vertical component v2 fy. So as I'm looking at the horizontal component, I see that I have my adjacent side and my hypotenuse. So remembering SOHCAHTOA, if I have my adjacent side and my hypotenuse, I'm going to use the cosine. When we get to the y direction, you'll notice that both my initial linear momentum terms went to 0, and so there's nothing on this side. That means that this term and this term have to cancel each other out, or need to be equal in their magnitude. And you'll notice that the linear momentum in the y direction for ball 2, I use the sine trig term, and that is where I have the opposite side and the hypotenuse, so I use sine. Now another thing that all of my terms in both the x and the y direction share is the mass. Remember, these are identical billiard balls, so I'm going to divide both sides by the mass, and those will all cancel out. So let's rewrite it. So I've eliminated my mass variable, and of course we're looking for the final velocity of billiard ball 1, and we'll express that in magnitude and angle form, and that's part A and B. So let's reform our equations to solve for our objective variables here. Alright, so I've moved my terms around and I have an algebraic solution for the components of billiard ball 1's final velocity. So we'll go ahead and calculate these and get some answers and then move them into magnitude and angle form. Now there's something I want to highlight really quick. Notice that I've got a whole lot of subscripts on each of my terms here. That helps describe which velocity or which speed I'm talking about. So for this one over here, it's the speed of ball 1 in the final frame in the x direction. Here I have the speed of ball 1 in the final frame in the y direction. Use your subscripts. They will keep the confusion to an absolute minimum so long as you are disciplined and consistent in how you use them. So we can take our components. I'm going to go to the next page. I'll paste them up there, and we'll put this into magnitude and angle form. All right, so we have our components here. Remember, we only have components now. The task given to us for part A was to find the magnitude of the velocity. So if we have our components and we need the magnitude, then we draw ourselves a triangle. Notice that I'm inverting it because it looks like our drawing here. We have our angle, we have our y component, and we have our x component, and we're looking for V1F. So if we have three sides of a right triangle, then we use the Pythagorean theorem. So we take our one side, and this happens to be our x side, we square it, we add it to the square of our y component, square root the whole thing, and we get the hypotenuse, or in this case, the magnitude of billiard ball number 1's final velocity. And we end up getting 1.9 meters per second. And this is 2 sig figs because if we look back at our problem, we've got 1, 2. Angles don't matter as much to us, but we have 2 up here as well. Okay, so 2 sig figs for this problem. And as we look at the magnitude during our check step, we expect the hypotenuse to be larger than both the component sides, and in fact they are. So this looks like a pretty reasonable answer. Now for part B, we need our direction. So we're going to find an angle with respect to the positive x-axis, just like we have listed right here. Now you may have seen on the suggested solution or the suggested problem solution that they use the arctan, but really you can use in any of the trig functions. That's because we now have all three sides. So we have our angle is equal to the arctangent, and if we remember our SOHCAHTOA, for the tangent function we need the opposite side divided by the adjacent side. Now I could have easily have just done the arc cosine, which would mean that we would need the adjacent side and the hypotenuse. Or I could have used the arc sine. And we would need the opposite side over the hypotenuse. So any of these would work. You would get the same answer for all three options. And we end up getting a final answer of 30 degrees. And of course, that's with respect to the positive x-axis. Now before we move on, I want you all to pay close attention to how I went through this problem. Did you all notice that I didn't put numbers in until the very, very end? If you really want to maximize your partial credit on any of the WPRs or MyRITs or the T, try to keep from putting numbers in until the absolute very end of a problem. So for this problem, I did put in numbers a little early, but from what you see on the solution, you just see variables for the most part in all of my equations. That shows the logical flow of where I'm going, and it's easy to track, especially with my disciplined use of subscripts. When you put in numbers, it's hard for us, the graders, to actually follow the flow of your logic. So again, I can't express this enough. Do not put in numbers until you've reached some type of algebraic solution. Okay, let's go on to part C. All right, part C. It won't make much sense to you now, but in a few lessons, we will discuss the conservation of energy. Now, all collisions conserve linear momentum. Now, this is going to be important when you get to different types of collisions and you try to think, oh, should I do conservation of linear momentum? Should I do conservation of energy? Which one should I use first? Always try to use conservation of linear momentum first. It depends on your given information, but start there because every collision conserves linear momentum. Now, not all collisions conserve kinetic energy. And you might be thinking, wait, the universe always conserves energy, and your thinking would actually be correct. But we have different forms of energy. We have translational kinetic energy. That's where we have a block sliding on a table going from point A to point B. We have rotational kinetic energy, where you just have something spinning. You can mix both of these types of kinetic energy and you have something like a ball that is both rolling or rotating and translating. Again, we'll get into this in a few lessons. We also have potential energy, and we can express, or a few examples of potential energy. We have gravitational potential energy. We have something like spring potential energy. We have electric potential energy. We have chemical potential energy. So lots of different options for potential energy, but for the most part, we're going to focus on the first three: gravitational, spring, electric potential energy when we get to our electromagnetic portion of the course. And lastly, we have thermal energy, which happens to be the culprit in most collisions, in that we conserve linear momentum but not kinetic energy. And the reason is that loss of kinetic energy from our just before frame to our just after frame is a loss of thermal energy to the environment. And so that's why it's really important when we say we have a closed and isolated system, that lost thermal energy can be accounted for in the form of non-conservative work, again, and a few lessons. But I just want to bring this to your attention so that you understand kind of what's going on. And when it does come up in a few lessons, you'll be like, oh yeah, I remember that. All right, so that's pretty much it for this problem. And I hope to see you tomorrow, ready for questions.